Have you ever considered that your perception of time, that steady march of seconds and minutes, might not be universal for everyone, everywhere? What if the rate at which time passes was not an absolute constant? Moving clocks appear to run slower due to a fundamental concept known as time dilation. This is a direct consequence of Albert Einstein's theory of special relativity, revealing that time is not an absolute, unchanging quantity, but rather is relative to the observer's motion. The core mechanism behind this remarkable effect lies into key postulates of special relativity. First, the laws of physics are the same for all observers in uniform motion. Second, and perhaps most crucially, the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. To illustrate, imagine a light clock where light bounces between two mirrors. For an observer at rest relative to the clock, the light travels a straight up and down path. However, for an observer watching this clock move past them, the light must travel a diagonal path to reach the mirrors. Since the speed of light is constant for both observers, and the moving light must cover a greater distance, the moving clock must tick slower to ensure the light still travels at its universal speed. This difference in distance covered for the light effectively means time itself is ticking slower for the moving system, as observed by the stationary viewer. Understanding time dilation means recognizing that your frame of reference profoundly impacts how you measure time. This is not just a theoretical curiosity but a practical consideration in our modern world. For instance, the accurate functioning of Global Positioning System, or GPS, satellites relies on accounting for time dilation. These satellites orbit Earth at high speeds, and their onboard atomic clocks experience a slight slowing relative to clocks on Earth's surface. If these time dilation effects were not corrected, GPS would quickly become inaccurate, making navigation systems unreliable. This phenomenon introduces us to the fascinating concept of spacetime, where space and time are interwoven into a single, four-dimensional fabric. The amount by which time slows down is governed by the Lorentz factor, a mathematical expression that depends on an object's velocity relative to an observer. The faster an object moves, the larger its Lorentz factor becomes, and the more pronounced the time dilation effect. While typically negligible at everyday speeds, this effect becomes significant as objects approach the speed of light, showcasing the universe's counterintuitive yet elegantly consistent rules. Ultimately, time dilation reveals that time is not a separate, universal backdrop but an integral part of the fabric of the universe, directly influenced by motion. By embracing this concept, we gain a deeper appreciation for the interconnectedness of space and time, enhancing our understanding of fundamental physics and the very nature of reality itself.